It's a pleasure to have Peter Shor this morning from MIT, who will tell us about quantum money and what, well, we should not invest or invest.
Okay. So I'm going to be talking about quantum money. This is joint work with Andre Kazin, who's a grad student at MIT, and Jonathan Liu, who's an undergraduate at Harvard. What's all this beeping? Okay. All right, so I'll keep on going. What I'm going to first talk about is the motivation and history of quantum money. And after that, I will get to the background you need on lattices. And finally, I'll give you a very brief sketch of my proposed protocol for quantum money. So one big problem with money is that you can make copies. So if you're a counterfeiter, you can make a lot of, illicit money that you can then convert into real money. So quantum states satisfy the no cloning theorem, which says you cannot make a copy of an unknown quantum state. And you'd think that this would immediately let us use quantum states for money. So this was Wiesner's idea. He had it back in 1969, and it took like 14 years for it to actually get published. And then it wasn't even in a real scientific journal. It was in the newsletter of the ACM Special Interest Group on ACT, which is, I forget what it stands for, but it's really computer science theory. So his scheme has some drawbacks, but it turns out that it's a lot harder to come up with a quantum money scheme that doesn't have drawbacks. So here's Wiesner's scheme. And so in each bill, there's a sequence of quantum states in one of two complementary bases. So either it's up vertical or horizontal, or it's right diagonal and left diagonal. And from this density matrix calculation, you can tell that anybody who has the sequence of states but doesn't know which bases they're in cannot tell which bases the states were prepared in, which means that by the quantum no cloning theorem, if they don't know the polarization of these states, they cannot copy them. And an interesting thing to note is that Wiesner proposed this well before the no cloning theorem had been formally proven, but it's clear that he somehow knew it intuitively. So what are the problems with Wiesner's money? Well, the Mint, which is the whatever organization put the polarizations into the bill, knows the polarizations and so can easily check it. But what we would really like is the merchant to be able to verify that the bill is legitimate without sending it back to the Mint. So you could tell the Mint the quantization axes and the eigenvalue of each qubit. And if he knew that, the Mint could verify the money. But if the merchant knew that, they could also make new bills exactly like the ones they got. And you could try giving, just some of the polarizations to the merchant, but then a coalition of merchants could get together and make fresh bills. So this scheme, we'd like something better. And now I'm going to talk to a little bit about my motivation for quantum money and cryptography background. So for many years, cryptography was done with ad hoc crypto systems, and many of these were eventually broken. So over the last few decades, cryptography has become much more mathematical, and theoretical computer scientists now try to prove the security of crypto systems. And there are two kinds of proofs of security in cryptography. There's security through information, and there's security through complexity. So a crypto system is informationally secure if you can prove that no matter how powerful a computer an adversary has, it will not be able to break the crypto system. And this is essentially because the information that the adversary has does not contain enough information to break the code. So it's a Shannon-type information theoretic proof. And for computationally secure crypto systems, you show that the security of the crypto system relies on the difficulty of solving some computationally hard problem. So for example, RSA relies on the difficulty of factoring large numbers. And there are two drawbacks with these. The disadvantages of the informationally secure system, crypto systems, is that very few cryptographic primitives can be accomplished with informational security. So for example, one-time pads are informationally secure. BB84, quantum key distribution, can be proved informationally secure, but there's no kind of private key or public key crypto system that you can prove is informationally secure. And so modern cryptography cannot use informationally secure crypto systems. The problem with computationally secure crypto systems is that theoretical computer scientists have not been able to prove pretty much any problems are hard. They have very good evidence that NP-complete problems are hard, but you can also prove that you cannot base a public key crypto system, or actually on an NP-complete problem. In fact, you can't base any crypto system on an NP-complete problem. So you have to choose some hard problem and try to hope that it really is hard. And the history of cryptography is littered with crypto systems that have been broken. Even ones that were supposedly based on NP hard problems have been broken. So the BB84 protocol for quantum key distribution can be proved informationally secure if you assume that quantum mechanics obeys the laws that we think it does. So this solves a task which is impossible to perform with an informationally secure protocol and classical computing. So the way that I started thinking about quantum money was I asked myself, are there any cryptographic tasks that a quantum computer might perform with computational security, but are impossible for a digital computer to perform? And so I came up with the task of quantum money. So we would like one of the players in the protocol, who we will call the mint, to be able to make a quantum state and a verification test. And the quantum state has a serial number attached. And that's, let's see, do I have a, yeah, that's I here. And the verification test depends on the serial number. So that first, the quantum state passes the verification test. I should probably have said with very high probability. Second, the test does not destroy the quantum state. And third, an aspiring counterfeiter who holds both the quantum state and who knows the protocol cannot produce a state of two quantum systems that both pass the test. So you have to be sure that you have to make sure that the case of the counterfeiter does not hold the state and know the protocol, because there are, I guess, quantum money protocols where you can prove that if he just knows the protocol, he can't break it, and if he just knows the quantum state, he can't break it. But if he has the state and knows the protocol, then he can break it. So this is a little more complicated than you might think at first. So there have been a bunch of proposals for computational secure quantum money, and two of them have been broken, or at least partially broken. So what you'd really like is a proposal for computational secure quantum money that depends on some hard problem which people really believe to be hard, and not one of these problems which is, I guess, just a problem that someone has come up with and they don't know whether it's hard or not, and nobody has really spent any serious time trying to solve the problem. So this is what we propose. We have a quantum money protocol that is based on lattice cryptography. And in fact, we believe that not even the mint can efficiently make another copy of the quantum state with the same serial number. So the mint is not does not have a secret that lets it make the quantum money, it has, it comes from the properties of quantum mechanics and measurement, and you'll see how this happens a little bit later in the talk. And what we can show is if the money can be duplicated, then if you have a random lattice where you know one short vector, you can find a second short vector in it. And this is believed to be hard by cryptographers. So how does our lattice quantum running protocol work? So what we're going to do is first going to talk a lot about lattices, and then we're going to sketch our first candidate for quantum lattice money, and then we'll explain why it can be broken. Now we'll sketch another candidate for quantum lattice money, and then we'll explain why it can't be broken either. And now we'll sketch a scheme that we think does work, although I wouldn't be absolutely sure that it works until we've completely written up the protocol and checked it carefully, because both of these two previous schemes broke at the last stages of our writing up the protocol. So, and there are a bunch more failed schemes that, some of which had ideas that went into the final scheme, but I won't talk about them in this talk. So what is the problem? The problem is finding a short vector in a lattice. So what is a lattice? It's a set of all integer combinations of n vectors in n dimensions. And the hard problem is given a basis of long vectors for the lattice. And these two blue lines, if you can see them, are supposed to illustrate that. They're not really a basis, but pretend they are. Then find a basis of short vectors for the lattice, like this little red basis. And of course, in 2 dimensions, it's incredibly easy. And in n dimensions, the best thing known is essentially the Lenstra, and Lovász algorithm called L cubed, which finds a basis that is 2 to the n times longer than the shortest possible coordinates, and specify them. There's exactly one way you can fill out the last coordinate to be in the lattice. So there are p to the n minus 1 lattice vectors in this cube. And assume p is a prime. I don't think it really has to be for anything, but it's much easier to work with if it is. Now, the dual lattice of a lattice is a very important concept. The dual lattice is a set of vectors which are perpendicular to all vectors in the lattice. And here we mean by perpendicular to x dot v is a multiple of p. So this is a scaled version of the dual. And the dual lattice has exactly one vector in each hyperplane. So the dual lattice is much, much, much sparser than the primal lattice. And in fact, this dual lattice is one-dimensional. Every lattice vector is a multiple of some generating vector. And these lattices are just as hard as ordinary lattices. Now, the nice thing about these lattices is you can define a quantum Fourier transform that takes vectors in the lattice to a superposition of vectors in the lattice. And here's the equation, which it looks just like the regular Fourier transform, so you don't need to worry about it. And the properties of the Fourier transform is if you have a large Gaussian superposition of lattice points around the origin, you get a small Gaussian superposition around each of the points of the lattice. And these standard deviations of these Gaussian superpositions are related by this formula. Now, if you start with a small Gaussian superposition, you get a bunch of large superpositions around each of the points of the dual lattice. And wait, that went backwards. Oh, no, it didn't. And now, so now if we have a Gaussian ball that's centered, but not at a dual lattice vector, but not at the zero dual lattice vector, you still get Gaussian balls around each dual lattice vector, but each Gaussian ball around the lattice vector has some phase attached to it, which you can see looks just like the formula for a Fourier transform. So now I'll tell you what our first algorithm was. We'll say the quantum money state is a Gaussian superposition of lattice balls around a single dual lattice vector W. And how can we create it? We can take a large Gaussian ball at the around 0, take the Fourier transform, now you get nearest dual, now you get small Gaussian balls around every dual lattice vector. And now you just measure using bounded distance decoding. This is something you can do if these balls are small enough to get a small Gaussian ball around a single dual lattice vector. And that's your quantum money state, this guy. And the serial number is going to be the dual lattice vector W. And you can see that the serial number is completely random because this measurement chose a random one of these Gaussian balls. So the serial number cannot be duplicated by this procedure. So why should you not be able to copy? So suppose you could copy. You could take a sample from the original, measure a point in the original, and a point in the copy, and now you get two lattice vectors, which are both close to W, and their difference is close to 0, and so it's a short vector. So why doesn't this protocol work? Well, the short answer is we don't know how to distinguish between having one lattice vector near W and having a Gaussian superposition of lattice vectors near W. And so someone who wants to counterfeit this money could simply measure one lattice vector from our small Gaussian ball and make arbitrarily many copies of that, and would pass all of the tests. Because, you know, we can't, it's indistinguishable from the real lattice money. So what's our second attempt? Well, we're going to start with V be the dual lattice ball with the first coordinate, dual lattice point with the first coordinate 1, and let W be the dual lattice point with W dot B equals 1, so inner product 1 with B. And now we'll let G of U be the small Gaussian ball centered at a dual point U. So the quantum money state will be the superposition of some sequence of Gaussian balls T plus J W. And the serial number here is T. And I should say that a measurement similar to the measurement I did before can actually create this state with a random T. So why is this a good candidate for quantum money? Well, let's consider the Fourier transform of the sequence that starts with a bunch of 1s, k over 2 1s, and has a whole bunch of 0s, and then another k over 2 1s. And what is the Fourier transform? Well, essentially, you want to sum j equals 0 to k over 2 pi kx, which looks like this. And nearly most of the mass, I think, say 50% of it, is between minus 1 over 4k and 1 over 4k. So now remember that if you had a small Gaussian ball centered at a point W, then when you took the Fourier transform, you got e to the minus 2 pi I v dot W over P as the sum of the amplitude on all the points around Gaussian ball V, which means that this is just a Fourier transform. So we're taking Fourier transforms of the Gaussian balls around points, and if our quantum money is this sequence of a T plus W adjacent balls, then by the same calculation as the Fourier transform on the previous slide, most of the mass is in Gaussian balls, which have the first coordinates between minus P over K and P over K. And on this picture, I've just illustrated the left half of the thing. So this is Gaussian balls around between 0 and P over K, which are the ones which most of the mass is in. Are what? What was your question? 1 over square root of K? It's 1 over K.
It's the sum for the quantum money, the normalization constant for the wave function.
Oh, this 1 over square root of J is the normalization constant, so that this vector is 1, and we have another hidden normalization constant for each of these Gaussian balls. So, and you're right, it's 1 over square root of K. Yeah. So that's a typo. So the Gaussian balls, when you take, when you take our quantum, when you take the state and take the Fourier transform, you get Gaussian balls around each of these points, and these Gaussian balls blur all these lattice points. So, I mean, they're all very well separated in n dimensions, but this picture is just in 2 dimensions, so they overlap a lot. And so how do we break this quantum money? Well, the quantum money state was this. Again, this is square root of k. And by Fourier analysis, to get most of the mass between minus p over 4k and p over 4k, an aspiring counterfeiter needs to construct a counterfeit state with lattice point and at least a constant fraction of the k Gaussian balls. But he can only measure a point in one of the Gaussian balls. So to be able to place a point in all the Gaussian balls, you would think that he needs a lattice vector that takes you from one Gaussian ball to the next Gaussian ball. And then he can measure a point from one Gaussian ball and construct a point in all of the other Gaussian balls. So is there such a vector? Yes, there's a magic vector, and we can let E1 be the vector with a 1 in the first coordinate and zeros in the other. And now W minus E1 dot V is, well, B dot W was 1, and E1 dot V is 1 because the first coordinate of V was 1. So W minus E1 is 0, and that means W minus E1 is an L. And W minus E1 is very close to a dual lattice vector W. So that means that you can go from one Gaussian ball to the next. And that doesn't tell you that the money is actually broken, but in fact, if you do all the calculations, you find that the money is broken. So what do we do? Well, I have 3 minutes left, and there's not enough time to explain how exactly it works. But this is right. This is the what I just said in the previous slide, the width of the Gauss. Okay, yeah, because the vector that takes you from one Gaussian ball to the next is E1, you can only get order of sigma points in Gaussian balls, because when you go from one Gaussian ball to the next, you've moved the point that takes you from one to the next is W minus E1, and it's 1 unit further from the center of the Gaussian ball than the earlier one. So once you take O of 6 sigma Gaussian balls, you move to the edge of the Gaussian ball, and now it's no longer good quantum money. So that means you can't concentrate the mass in a smaller region than O of P over sigma. And you'd think that you might be able to do, to take enough Gaussian balls to concentrate in O of P over sigma. But even if you have all the centers of the Gaussian balls in a very small region, the width of these Gaussian balls means you can't measure the peak better than O of P over sigma. And so, in fact, the money is really broken. So I want a very brief sketch in 3 minutes of what the final quantum money is. So instead of just looking at one coordinate to test it, you look at 2 coordinates. So you look at the first 2 coordinates. You use a random lattice L that contains the known short vector 2 minus delta and a whole bunch of zeros. And now delta has to be bigger than sigma, or must be much bigger than sigma. Well, much. It needs to be, say, 5 standard deviations bigger than sigma. So something that's delta from the center has a very small chance of appearing when you measure something in the Gaussian ball. And now what happens is you have more Gaussian balls that you construct a superposition of, which give you a complicated Fourier transform that you can check by just looking at 2 coordinates. And you also get more complicated magic vectors taking you from one Gaussian ball to the next. You have the original magic vector, and you have a second magic vector. And by characterizing these magic vectors, we can show that there's a way of constructing the quantum money so that an adversary cannot measure a single point and make a state that mimics the quantum money. And in fact, there's another argument that says if you can break the quantum money, you can find a second linearly independent short vector in L, not this one. And you shouldn't be able to do this with lattices, so we think this quantum money is secure. And I'll skip the one more detail and skip to the open questions. First, you want to show rigorously that you can't tell a Gaussian ball around a dual lattice point from a random point that was measured at. So we want to show, one question is, can you show that this original scheme for Gaussian money really doesn't work? Second, improve the quantum money scheme. So we haven't worried about the time and space required beyond making sure they're polynomial. So it's really very impractical right now. And if you improved it, you might get it to be slightly less impractical. And third, are these techniques used for other quantum cryptographic protocols? And two that come to mind are unclonable encryption. So you want to take your message, you want to encode it in a quantum state so that nobody who doesn't know the secret key can make a second quantum state that contains your message. And quantum copy, and of course, they need to be able to decrypt the message if and only if they have their secret key. And second, you want to do quantum copy protection. So you have a program and it, on a quantum computer and it runs, but nobody can copy it to make two copies of this program that run. Okay. Thank you.
Okay, so let me remind you that if you have a question, you're supposed to come down here, and let me also remind you that it's being recorded. So by coming down here, you are doing it as well. Any questions?
Hi.
The microphone. So if I understood correctly, the not invariant quantum money is as good as this one. Can you say, like, if there's any difference or compare the two?
Well, okay, so the not invariant quantum money is based on the, well, first, suppose you have two knots. Can you tell whether there are two planar diagrams that represent a knot? Can you tell whether these two diagrams represent the same knot? So if you can't do this, then the quantum money is secure. But it seems it's very probable that you can do this. So if you can do this, then the question is, suppose you have a knot, can you make the superposition of all the planar diagrams that have the same knot? And this, it's not at all sure that you can do this in, polynomial time with an algorithm, but it's also not, nobody has really looked at this problem. It's not clear that it's secure. So the advantage of this is that we can prove that it's secure as long as short lattice vectors is secure, and short lattice vectors is what the next standard in post-quantum cryptography is probably likely to be. So a lot of people have been trying to break it, and nobody has done it yet. And there are some theoretical reasons for believing it's secure, although maybe not very good ones.